Okay, students. So in Lab 1, you started with Experiment 1, which included the determination of the value of resistors. We did that by generating a data table and then a corresponding graph, the slope of which, the I versus V graph, was equal to the reciprocal of the resistance. Now let's continue with a different type of circuit where we have not one resistor, but two resistors. And let me show you what I mean. Let's say that you have our voltage, again, V, and this time you're going to two resistors. Here's R1, and there's R2. Let me designate these, R1, R2. There will be a corresponding current that will flow through that circuit. And given the arrangement, I think you can see, and you'll learn this in your upcoming class in physics, that whatever current goes into one end of a resistor has to come out the other end. If it didn't, then you'd have charges building up, increasing to the point where the thing would explode, metaphorically speaking. So we have to maintain this continuity of charge flow, and that means the same current comes out over here. Now the question becomes, how can we actually determine that current? Well, we can do so by realizing quite early on, and I'm going to extend this way over here so you can see it, that we can turn this circuit into an equivalent circuit that looks like same voltage, but this time, instead of having two resistors that are connected in the so-called series fashion, because the current flows sequentially or in series, first through one resistor and the second one, we can turn this combination of resistors into an equivalent series combination. As I told you, I like to use a lot of subscripts. They keep my mind on task. Once we have that value of equivalent resistance, we can compute the current. We know it has to be the same as the current over here. Now how can we do this? Well, actually it turns out it's quite simple. The first thing we notice is, and I'll do this in a different color just to highlight this for you, we know that there's going to be a voltage that exists across this resistor and a different voltage perhaps across this resistor. The point being, and let me back this up a little bit, I want you to think of electrical circuits analogously to gravity. Let me explain. Imagine that I have a mass, M, and this is ground, the ground level, and I lift it up. It gains potential energy, gravitational potential energy, and as it moves along horizontally, as long as there's no change in elevation, there's no loss in the original potential energy. But then as it descends to different heights, it begins to dissipate the original energy it started off with. Nonetheless, what we can say is whatever gravitational potential energy I placed in that system, it will, through a series of changes of elevation, decrease that potential energy so that the sum of these drops here will equal the sum of the elevations here. Now, this isn't gravity, but it's electricity, but the equations are the same. Whatever charge happens to flow through this battery, it will gain not gravitational potential energy, but electric potential energy. And likewise, as it descends or drops through each resistor, there will be a drop in potential electric energy. The sum total of which, whatever we lose here plus here, must equal what we gained originally. So I'm going to write this as V1, and I'm going to write this as V2. Now, what I can write here is the following. V, our original voltage in both cases, must be equal to the drop that we have here, V1, plus the drop that we have here, V2. Now, let's use Ohm's law, our good old friend Ohm's law. You remember this. I equals the current that flows through a resistor equals the voltage across that resistor divided by the value of the resistance. So I'll just write that down, I equals V over R. We can rearrange this equation, and this will become important when we go to do the following, finding the voltages. V, therefore, will be equal to IR. We're going to use that relationship now. So, V1 must equal the current that flows through that resistor, I, times R1. V2 must equal same I times R2. Now, we can simply replace these two values, V1 and V2, into the above equation. Watch what happens if we do so. We get I R1 for V1 plus I R2 for V2, all of which has to be equal to V. Well, what is V equal to? What is V equal to? V is equal to I times R, correct? But this is R equivalent, so watch what I'm going to do. I, R equivalent series is equal to the sum of the voltage drops, which we have here. Well, immediately I think you can see that I is common to both sides, and look what we end up with, this nice relationship. R equivalent series is equal to the sum of the resistors that we have. And we're going to put a box around that to remind you that this is an important result, one that you're going to try to prove. And by the way, it doesn't matter whether we have 2 resistors or 1,000. The point is that the equivalent series resistors is nothing more than the sum of the individual resistors that we have. We can go a little further with this, because remember I just told you that the total voltage that we have across here is equal to the voltage loss here plus the voltage loss there. What we can do, and I just want to check my results over here, make sure I'm not making any errors. All right, I have our equivalent, good. The fact that the current is the same in both of these resistors allows me to make the following calculation. And please watch this carefully. The current is the same in both of those resistors, namely I is the same in both of those resistors. Well, what is I equal to? We could calculate it using Ohm's law, and we would end up with V1 divided by R1. That would be the current. Well, that's also the same current that flows through here, which would be V2 over R2. And I think you can see what will happen next, but in case you don't, let me show you. I can simply gather terms on opposite sides, and I finally end up with the following relationship. Watch carefully. V2 divided by V1 is equal to R2 over V2. And that is an important relationship. Let me say it verbally. And you know what? I messed that up. Sorry about that. R2 over R1. Let's state that verbally. The ratio of the resistances will always be equal to the ratio of the voltages that are across there. You're going to be asked to prove that relationship in the series experiment. You'll have a data table, and one of the columns will have you compute the ratio of the voltages and the ratio of the resistances. Theoretically, they should be identical, and you'll be able to find out if that's true. All right, we're going to move on finally to parallel resistances in a moment.